My dear students, welcome back to our channel. In this video, I will be explaining the BSc second semester subject Chemistry as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Tips for preparation. Structure-based questions like XCF4, XCO3, ICL, I are visual and important. Practice drawing. Focus more on redox behavior of oxyacids for variety and reaction-based problems. D-block characteristics like magnetic and catalytic properties are foundational and must be understood clearly. For noble gases, Clathrates and Xenon compounds are must-read topics. Unit 1 first important short question is: what are transition elements? Why do they show variable oxidation states and magnetic properties? Answer: transition elements are D-block elements found in the middle of the periodic table, groups 3 to 12. Examples include iron, Fe, copper, Cu, and chromium, Cr. They are called transition because they act as a bridge between metals and nonmetals. Why do they show variable oxidation states? They have partially filled d orbitals, so they can lose different numbers of electrons. For example, iron, Fe, can form both Fe superscript 2 and Fe superscript 3 ions. This gives them the ability to show multiple oxidation states. Why do they show magnetic properties? They have unpaired electrons in their d orbitals. These unpaired electrons create a magnetic field, which makes elements like Fe, Co, and Ni magnetic. Easy tip to remember: D-block is equal to different states plus demagnetism. These properties make them useful in magnets, catalysts, and colorful compounds used in paints and industries. Next important short question is: to write a note on Clathrate compounds of noble gases. Answer: Clathrate compounds are like cages or boxes made by water or other molecules which trap noble gas atoms inside them, like putting a cricket ball inside a net without tying it. Noble gases like argon, Ar, krypton, Kr, and xenon, Xe, can form clathrates under high pressure and low temperature. Example: xenon clathrate with water Xe gas gets trapped inside ice-like cages made of water molecules. It looks like a solid, but inside, the gas is safely packed. Why special? Noble gases are inert, do not react easily. But clathrates are physical traps, not chemical bonds. Easy trick to remember: clathrate is equal to cage plus gas. They are used in gas storage, separation, and in nuclear chemistry for trapping radioactive gases. So, noble gases may not bond easily, but they can still be caught in a cage. Next important short question is: 3. Write the anomalous behavior of He2. Answer: helium, He, is a noble gas, but it shows unique, anomalous behavior, especially in its liquid form He2, also called liquid helium-4. What is He2? When helium is cooled below 2.17 K, minus 271 degrees Celsius, it becomes liquid helium-2, which is a superfluid. Superfluid means it can flow without friction. It can climb walls of containers. It can pass through very tiny holes which normal liquids can't. Why is this behavior anomalous, strange? No other element shows such superfluidity. Helium doesn't solidify even at 0 K under normal pressure. Very rare for any element. Easy trick to remember: He2 is equal to helium's magic water. It flows like magic, no resistance, no stopping. Uses in cooling magnets in MRI machines and in scientific research at very low temperatures. Next important short question is 4. Give the structures and hybridization of XeF4 and XeF6. Answer. Xenon, Xe, is a noble gas, but it can still form compounds like XeF and XeF with fluorine due to its large size and available empty orbitals. XeF xenon tetrafluoride. Hybridization, sp superscript 3d superscript 2. Structure, square planar. Xenon forms 4 bonds with fluorine and has 2 lone pairs of electrons. The lone pairs sit opposite each other, keeping the shape flat like a chessboard. Tip XeF is equal to 4 Fs plus 2 lone pairs, 6 regions sp superscript 3d superscript 2. XeF xenon hexafluoride. Hybridization, sp superscript 3d superscript 3. Structure, distorted octahedral, not perfect due to 1 lone pair. Xe bonds with 6 fluorine atoms and keeps 1 lone pair. This lone pair makes the shape slightly bent or distorted. Tip XeF is equal to 6 Fs plus 1 lone pair is equal to 7 regions sp superscript 3d superscript 3. Easy to remember. Xe plus F is equal to fun shapes. Square for 4, bent for 6. Next important short question is 5. Write a note on copper triad. Answer. The copper triad includes copper, Cu, silver, Ag, and gold, Au. They are found in group 11 of the periodic table and are part of the D block or transition elements. Why called a triad? They have similar properties like good conductors of heat and electricity, high luster, shine, used in coins and jewelry, oxidation states. They commonly show +1 and +2 oxidation states. Example: Cu and Cu superscript 2, Ag, Au and Au superscript 3. Special features: gold, Au, is very unreactive and doesn't corrode easily. Silver, Ag, has the highest electrical conductivity. Copper, Cu, is widely used in wires and electronics. Easy tip to remember. CuAgAu is equal to coins, shine and wires. They are called coinage metals because they were used in making coins in ancient times. Next Unit 1. Long questions, most important. First important long question is: what are transition elements? Explain magnetic and catalytic properties of transition elements. Answer. Transition elements are the elements found in the D block of the periodic table, groups 3 to 12. They are called transition because they form a bridge between the S block, alkali and alkaline earth metals, and P block, nonmetals and metalloids. Examples include iron, Fe, copper, Cu, chromium, Cr, nickel, Ni, and zinc, Zn. Why are they special? They have partially filled d orbitals, which give them unique properties like variable oxidation states, formation of colored compounds, magnetic properties, catalytic activity, ability to form complex compounds, magnetic properties. Transition elements have unpaired electrons in their d orbitals. These unpaired electrons cause magnetism. The more unpaired electrons, the stronger the magnetic behavior. Example: iron, Fe, has unpaired electrons and shows strong magnetism. Zn, zinc, has no unpaired electrons, so it is not magnetic. Tip to remember: more lonely electrons is equal to more magnetism. Catalytic properties. Transition metals are excellent catalysts. A catalyst speeds up a chemical reaction without being used up. They act as catalysts because 1. They can easily change oxidation states, which helps in electron transfer. 2. Their surface can adsorb reactants, making reactions faster. Examples: Fe is used in the Haber process to make ammonia NH. VO, vanadium pentoxide, is used in making sulfuric acid. PT, platinum, is used in car catalytic converters. Easy tip: transition metals is equal to reaction boosters. Summary: transition elements are important in industry, electronics, and everyday life because of their magnetic and catalytic powers. Memory trick: transition is equal to transform. They transform electricity, magnetic, and reactions, catalysts. Next important long question is: to explain the classification, preparation, and structure of interhalogen compounds. Answer: interhalogen compounds are chemical compounds formed between two different halogens F, Cl, Br, I, at. For example, ClF, BrF, ICl, if. They are more reactive than individual halogens, except fluorine, and are often used as fluorinating agents. Classification of interhalogen compounds. They are classified based on the number of halogen atoms. 1. AX type, 1 example, ICl, BrF. 2. AX type, 1 example, ClF, BrF. 3. AX type, 1 example, BrF, if. 4. AX type, 1 example, if. A is equal to larger halogen, X is equal to smaller, more electronegative halogen, like F. Preparation of interhalogen compounds. They are prepared by direct combination of halogens in required ratios. Examples: Cl plus 3F to ClF. Br plus 5F to BrF. I plus 7F to F. Usually, the more reactive halogen, like F, is added in excess. Structure of interhalogen compounds. The shape of interhalogens depends on the number of bonding and lone pairs around the central atom. ClF, AX, T-shaped, 2 lone pairs. BrF, AX, square pyramidal, 1 lone pair. If AX, pentagonal bipyramidal, no lone pair. These structures are explained using VSEPR theory, valence shell electron pair repulsion theory. Easy tips to remember. Inter is equal to between plus halogens is equal to halogen friends combine. More F is equal to more reactive. More X is equal to more lone pairs is equal to bent structures. Summary. Interhalogen compounds are formed by combining two halogens, classified by their formula type, AX, etc., and are prepared by direct reaction. Their shapes are predicted by VSEPR theory, and they are highly reactive. Next important long question is: 3. Explain xenon halides and oxyhalides. Answer. Xenon, Xe, is a noble gas, and noble gases were once thought to be inert, non-reactive. But xenon can form compounds, especially with fluorine and oxygen, due to its large size and available empty orbitals. Xenon halides. Xenon forms halides mainly with fluorine, F, not with Cl, Br, or I because fluorine is highly reactive. There are 3 xenon fluorides. 1. XCF, xenon difluoride. Shape, linear. Hybridization, sp superscript 3d. Structure, Xc in the center with 2 F atoms on sides and 3 lone pairs. 2. XCF, xenon tetrafluoride. Shape, square planar. Hybridization, sp superscript 3d superscript 2. 4 F atoms and 2 lone pairs. 3. XCF, Xenon hexafluoride. Shape distorted octahedral. Hybridization sp superscript 3d superscript 3. 6 F atoms and 1 lone pair. Easy tip: Xc plus F is equal to funny shapes. Xenon oxyhalides. These are compounds of xenon with both oxygen and fluorine. Examples: 1. XeOF, xenon oxydifluoride. Shape bent or T-shaped. Contains 1 oxygen, 2 fluorines, and 2 lone pairs. 2. XeOF, xenon oxytetrafluoride. Shape square pyramidal. 1O, 4F, 1 lone pair. These are formed by partial hydrolysis of xenon fluorides. For example, XeF plus HO XeOF plus 2HF. Easy trick to remember. Xenon plus fluorine is equal to XeF family. Xenon plus oxygen plus fluorine is equal to XeOF family. Summary: xenon halides, XeF, 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 have different shapes and hybridizations. Xenon oxyhalides, XeOF, XeOF, formed by reacting XeF with water. These compounds broke the rule that noble gases can't form compounds. Next important long question is: 4. Write the electronic configuration of the first transition series, 3D series. Explain their variable oxidation state and catalytic properties. Answer: First transition series, 3D series. These are the elements from scandium, Sc, to zinc, Zn, in period 4 of the periodic table. Their atomic numbers are 21 to 30, and they involve the filling of the 3D orbitals. Electronic configuration. Element symbol configuration. 21 Sc, Ar, 3D superscript 1 4 S superscript 2. 22 T, Ar, 3D superscript 2 4 S superscript 2. 23 V, Ar, 3D superscript 3 4 S superscript 2. 24 Cr, Ar, 3D 4 S superscript 1 exception. 25 Mn, Ar, 3D 4 S superscript 2. 26 Fe, Ar, 3D 4 S superscript 2. 27 Co, Ar, 3D 4 S superscript 2. 28 Ni, Ar, 3D 4 S superscript 2. 29 Cu, Ar, 3D superscript 1 4 S superscript 1 exception. 30 Zn, Ar, 3D superscript 1 4 S superscript 2. Variable oxidation states. Transition elements can lose different numbers of electrons from 4s and 3D orbitals. This gives them multiple oxidation states. Example: iron, Fe superscript 2 and Fe superscript 3. Manganese, Mn plus 2 to plus 7 oxidation states. Tip to remember: d orbitals is equal to dynamic oxidation. Catalytic properties. Transition metals act as good catalysts. They can donate or accept electrons, helping other molecules to react. Examples: Fe in the Haber process makes ammonia. VO in contact process makes sulfuric acid. Ni used in hydrogenation of oils. Tip to remember: transition metals is equal to reaction boosters. Summary: 3D series includes Sc to Zn with gradually filling 3D orbitals. They show variable oxidation states due to flexible d and s electrons. They are great catalysts in industry because of their electron exchanging ability. Easy line: 3D elements is equal to many charges plus fast reactions. Next important long question is: 5. What are pseudohalogens? Compare their properties with halogens. What are pseudohalogens? Pseudohalogens are chemical groups or molecules that behave like halogens, F, Cl, Br, I, but are not true halogen elements. They can form similar types of compounds, like salts, acids, and covalent molecules, and show similar reactivity. Examples of pseudohalogens: 1. Cyanogen, Cn. 2. Thiocyanogen, SCN. 3. Azide, N. These can form pseudohalide ions like Cn, SCN, N. Just like halide ions Cl, Br, etc. Similarities with halogens. Property halogens, example, Cl. Pseudohalogens, example, Cn. Exist as diatomic gases Cl, Cn. Form salts NaCl, NaCN. Form covalent molecules HCl, HCN. Act as oxidizing agents yes, yes. React with metals yes, yes. Example: Na plus half Cl, NaCl. Na plus Cn, NaCN. Differences from halogens. Feature halogens, pseudohalogens. True elements yes, F, Cl, Br. No, they are compounds. Found in periodic table yes, no. Natural occurrence found in nature, mostly made in labs. Easy tip to remember. Pseudo is equal to fake, but acts real. Pseudohalogens are chemical imposters. They behave like halogens, but are made of multiple atoms. Summary: pseudohalogens are compounds that look and act like halogens. They form similar salts and acids, show oxidizing nature, and bond with metals. They are not elements, but molecules, example, Cn, SCN, N. Used in organic chemistry and explosives, like sodium azide in airbags. Memory line: pseudohalogens is equal to halogen copycats with real powers.